Hey guys, Mr. Gardner here again. Today we're going to be learning about the Pythagorean Theorem. So our objective for today is that I can find a missing side of a right triangle using my knowledge of square roots with 80% accuracy. So that's what we're trying to accomplish with today's lesson. Before we do, we should just do a quick little mini history lesson on Pythagoras. Pythagoras was a math wizard from a long time ago. So he was really into doing math because there wasn't a lot of other stuff to do. So he wasn't able to spend his days watching Netflix, dancing away on TikTok, or owning sweaties on Call of Duty. Instead, he was left to his thoughts and to play around with math. Well, all that playing around really paid off because he came up with a lot of the most impressive theorems that we still use today in math. And this was 2,700 years ago, so a long time ago. And he was just messing around, playing with numbers, and he figured out this really cool theorem that we call Pythagorean Theorem. So what the Pythagorean Theorem says is that for any right triangle with sides A and B and hypotenuse h, the square of the hypotenuse is equal to the sum of the squares of the other two sides. This is a very profound discovery he made. I'm sure he made it just by, drawing figures in the sand or whatever he used to write. I know it wasn't the same thing I'm using. But it was a very interesting formula that he came up with. It really helped mathematical foundations move into trigonometry, and from trigonometry into calculus. So what he was saying was, if you look at these triangles, is that if you take the square of this side, which is called the perpendicular side, and you take the square of the base, which is the bottom, and you add those things together, so if you take a squared and you add that to b squared, every single time you do this on a right triangle, this diagonal length is equal to those two squared. Its square is equal to that. So that's a really profound discovery. I mean, it works for every single triangle. That's a right triangle. Okay, and when I say right triangle, we're talking about triangles that have the right angle in the corner here. All right? And the easiest way to remember hypotenuse is it's the side that's across from the right angle. It's the only one that's across from the right angle. So the weird name is the side across from the right angle. Okay, so that'll help us. The base and the perpendicular side are the ones that are always connected to the right angle. Okay, we would call those adjacent to the right angle. All right, so if that helps, these are adjacent, and the hypotenuse is across from the right angle, if it helps you remember where those are located. So in looking at these, there's a few of them that we consider like special cases. They're ones that help us figure out other bits of math. Okay, and it's just because they have perfect pairings. They go together so well that it's easy to calculate them. So that's a case where like we have our perpendicular side is 3. Our base is 4. Then it makes it really easy to find this hypotenuse side, the side that's across from the right angle. And if we take a look at the math, if we use this theorem, it's 3 squared plus 4 squared is equal to some number squared, right? And so we can look at 3 squared is 9 plus 4 squared is 16 equals some number squared. Okay, and now we can look at that. So we're beyond really using blank, so we really can just call this h squared and h squared here. So we get that 25 is equivalent to h squared. And we know from solving one-step equations that if we have a squared number and we're trying to solve for it, we take its square root. Okay? And so then we got to really think about, if we do it on one side, we do it on the other side. And then that tells us that h squared, the whole term, has to be the same as whatever the square root of 25 is. Well, 25 is one of our perfect squares, so we know that that's 5. So then we know the square root of h squared equals 5. Okay, and so then we can think Well, the square root of h squared is really h, right? Because anything squared is just itself times 2. So its square root is h. So that means 5 equals h. All right? And then we can just check our math. So 9 plus 16 equals 25, right? And this is 3 squared plus 4 squared equals 5 squared. So we can see that 25 equals 25, then that is true. So not every case we're going to look at is going to be perfect, but the theorem still holds even if the cases aren't perfect. So let's take a look at what it looks like when maybe we have a triangle that's not in the perfect trio like the 3, 4, 5 triangle is. Okay, but we can still use our knowledge and understanding of square roots to figure out these missing sides, or at least get close. So let's say we have a 5, 7 unknown triangle. Okay, and again, if we remember the perpendicular, this is A, this side's B, so A equals 5, B equals 7. H is unknown. Okay, you may see this sometimes referred to as C, but I'm going to keep it as H right now because it makes more sense. H, hypotenuse. We're going to just keep it that way. So by the theorem, we know that A squared plus B squared is going to equal H squared. So we know A is 5, we know B is 7, we don't know H. So we have to do a little bit of math. So we know 5 squared is 25 because we memorized the first 12 squares, I would hope. And we know 7 squared is 49. We still don't know what this one is. All right. Now again, we can do our math, do a little scratch work over on the side here. So we have 49 plus 25. We get 4 and a 1. And we have 2 plus 4 is 6 plus 7, 74. So then we know 74 is equal to h squared. Well, it still doesn't tell us what h is, right? But again, like this problem up here, we take the square root of both sides so we can get the h by itself. So then we have h equals the square root of 74. I know what you're thinking. You're like, well, now, Mr. Gardner, come on now. This isn't one of those squares we should have memorized. Well, you're right. But in the last lesson, we did talk about how to approximate squares. So if we were paying attention and we're thinking about our table, and I'll just put a little piece of it, we have 7 is 49, 8 is 64, 9 is 81, and 10 is 100. All right, then we can think about where this value actually lies. Okay, so we're looking for the square root of 74. So then we could think of that as being somewhere in here, right? It's between these two numbers. So we know the square root of 74 is going to be bigger than the square root of 64, and it's going to be smaller than the square root of 81. So then that tells us that the square root of 74 is going to be in between 8 and 9. So if we know that the square root of 74 is in between these two numbers, all right, then it makes it a lot easier for us trying to approximate it. So let's make a number line so we can see a little bit better where that number might be. So let's kind of lay two number lines on top of each other. So we know that this is the square root of 64, which is 8. And we know this over here is the square root of 81, which is 9. All right, and so what we want to do is we want to find this middle point, which we know between 8 and 9 is 8.5. So we want to find that by just looking at the distance here. So between 64 and 81, the middle of that, well, we can find its average, right? So we can add those two numbers and we can divide by 2. So if we add these two numbers, which I've done right here actually, we get 145. We divide that by 2, we get 72.5. Okay, so then we know that the square root of 72.5 is going to be right in between these two numbers. Okay, and so if we look at that, then we can see now that in between that is 8.75 is in between those. Okay, but the square root of 74 is really close to this, so it's probably right in between this. All right, and this number, because that's only like 8 away, so this is about 76 or some, around 76. So 74 is going to be closer to this direction. So we could say the square root of 4 is probably about 8.6. So that would be a good estimate for it, 8.6. And we can check our math by just multiplying 8.6 twice, because that's going to be what a square is. 6 times 6, 36. 6 times 8 is 48, plus 3 is 51. Put in our 0. We do 8 times 6 again, 48. Bring a 4 up here. 8 times 8 is 64, plus 4 is 68. Okay, we do that math. We get 6. We get 9. We had 2 decimal places in, so we'll put our decimal here. 5 times 8 is 13, so 3, 1. 73.96. So that's really close to 74. So 8.6 is a good approximation for the missing side of this triangle.